Alright, this video is going to be a discussion of crystal field theory, which is our accepted theory for describing the bonding that occurs between ligands and metal ions in a complex or a complex ion. So the assumption of this theory is that we're going to have splitting occurring between the d orbitals of the metal ion due to metal ligand electron repulsion. So what I want to do is start with a simple octahedral case, and we'll come back and we'll tell you a little bit more about the other geometries, but we can do a simple derivation for the octahedral case. So in an octahedral geometry, what we have are a set of Cartesian coordinates, x's, y's, and z axes here. And to get the 6 ligands in around the metal ion, we're going to bring a ligand in around each axis here. So 2 ligands per axis, 2 per x, 2 per y, 2 per z. So what we want to do is we want to look at how those ligands are going to interact with the individual atomic d orbitals associated with the metal ion. So what we have here are the individual d orbitals for our metal ion. So we go back and we need to remember from bonding what those d orbitals look like. So you remember that there are 5 different ones. We have a dxy, a dxz, a dyz, a dx squared minus y squared, and also a dz squared. And each of these is going to have a different orientation in space and a different number of lobes and this sort of thing. So this is review from bonding. You learned these orbitals back in bonding. So what we want to do now is we want to bring the ligands in along the axis, as I've shown here, and we want to see whether there's going to be any kind of overlap and thereby repulsion between the ligands and the orbitals themselves. So let's start with the dxy. So I'm going to be bringing in 4 ligands here, 2 along the x-axis, 2 along the y-axis. We'll also have ligands coming in along the z-axis, but we don't worry about those because we see that the orbitals now are orienting along the xy plane here. So we'd assume very little, if any, repulsion along the z-axis, which is coming out of the board at you. So in this particular case, what we see is that there's very little, if any, overlap between these orbitals and this ligand. So we'd assume this to be a low energy situation. There's very little repulsion here. Now we can do the same thing with the dxz and the dyz. In this case, I'm bringing my ligands in along the x-axis and also along the z-axis. We also would have ligands coming in along the y-axis, which is coming in out of the board here. And in this particular case, we see again that there's essentially no or very little interaction between these ligands and the orbitals themselves. Again, we can do the same thing with the dyz orbital. We'll bring in our 4 ligands in the same sort of manner here. And again, we'll see that there's very little, if any, interaction or repulsion between the ligands and the orbitals. Now, as we come down to the 2 different orbital orientations here, the dx squared minus y squared and the dz squared, what we're going to find is we bring the ligands in this case along the x-axis and the y-axis, is that we're going to get actual overlap here. We're going to get real repulsion between the ligand and the orbital itself. And when we have repulsion, the assumption is that's going to take us to a higher energy. Again, because electrons are repelling each other. We assume there are electrons associated with the metal orbital. We assume there are electrons associated with the ligand. When those electrons come into proximity with one another, they are going to repel. So we see here that this is going to be a high energy situation due to that repulsion, which we did not get in these 3 previous examples. Now also we can look at the dz squared case where we're going to bring our ligands in along the x-axis and the z-axis. And again, we're going to see that we're going to have another high energy repulsive situation here because of the interactions with the orbitals and the ligands here along the z-axis, and also with the donut of electron density around the x-axis and the y-axis, which is coming out of the board at you. So ultimately what we have is a low energy situation here, a low energy situation here, a low energy situation here due to minimal repulsion, and down here I have a high energy situation and I also have another high energy situation here. So ultimately, this means we are going to get some orbital splitting. So to see what we mean, let's take a look at what the actual energies of the d orbitals would look like in the case of an individual atom. So in this situation, this could be, for example, an iron atom or an iron ion, but there are no ligands surrounding that. And we know in this situation from chemical bonding that all 5 of the orbitals are degenerate, meaning they lie at the same energy. All right? Now, if I have the complex now, we see that we have varying degrees of repulsion occurring here, 3 low, 2 high. So ultimately what happens is I'm going to split these d orbitals into different energy levels. So I'm going to have 3 of them occurring at lower energy, which I'm going to put down here, and then I'm going to have 2 more of them occurring at high energy, which I'm going to represent again at a higher potential energy. So we see here now that there is a splitting difference in energy between these ligands. And the energy difference between them is now going to be termed delta, which is sometimes called the crystal field splitting energy. So ultimately, what we see here is that we're going to have a split set of orbitals, and now the next question becomes, how are we going to determine what corresponds to the value of delta? And we will have rules for doing that, which we'll take up next. All right, so we just saw in the case of the octahedral complex, we ended up with 5 split d orbitals. So in this case, we had 3 d orbitals at low energy with minimal repulsions. Those would be the dxy, the dyz, and the dxz. And then we had 2 more orbitals that were at higher energies due to repulsion. So those are the dx squared minus y squared and the dz squared. And we saw also that we had a particular crystal field splitting energy, which we call delta here. And we said that delta could vary based upon certain situations or circumstances. So the question then becomes, what factors control the magnitude or the size of delta? The primary one that we want to focus on in this course is going to be something based on the spectrochemical series. So what we're going to see here is that the ligands themselves can be divided either into strong field situations or weak field situations. Now the deal here is that a strong field ligand will induce a large delta. And in the case of a weak field ligand, we will have a small delta. And this in turn is going to tell us something about how we would populate the electrons into those orbitals, as we're going to find out. So strong field ligands involve things like cyanide and nitrite. And weak field ligands would be things like water, hydroxide, or fluoride ion. And the general break-off here, we're going to go with what the book says here, is that anything that's going to be water and to the right will be a weak field ligand. Anything to the left of water will be considered a strong field ligand. And again, in a quiz or an exam situation, I would give you this spectrochemical series, so you don't have to memorize this. So with the spectrochemical series in mind, let's take a look at 2 different examples involving the iron 3 ion, which in each case is going to be a D5 configuration, which you ought to be able to verify for yourselves. So let's look first at a strong field situation where the iron ion would be coupled with a strong field ligand such as cyanide, and then look at a weak field situation where the iron ion is coupled with a weak field ligand such as the chloride ion. So in the case of the strong field D5, notice that I have instituted a large delta, or gap in energy, between the low energy orbitals and the high energy orbitals. So in a situation like this, we need to think about how we're going to best occupy those orbitals. So in the first scenario here, the strong field scenario, I'm going to do what we normally do by starting out with the lower energy orbitals. And since these 3 orbitals are degenerate and lying at the same energy, I'm going to put the electrons all in at the same spin, 1 per orbital. Now at this point, since the delta is large, we have to ask ourselves whether or not we're better off distributing first and then pairing, or pairing and then distributing. Because the delta is large here, we're energetically better off to actually pair the electrons up in the lower energy orbitals as opposed to distributing them. So the last two electrons will now go in paired in the lower energy orbitals like this. So this leaves us with a situation where we have 4 paired electrons and 1 unpaired electron, all in the lower energy orbitals. Now let's move on to the weak field situation. In this case, again, we have a very small delta. So in the case of a small delta, we have to rethink how to populate those orbitals with electrons. So we're going to start the same way by putting our 3 electrons in, 1 per orbital, all spin up because those orbitals are degenerate. But now, because the delta is small, I'm going to distribute before I pair. So now those last 2 electrons are going to go into the top 2 orbitals here. So what we see is that in the D5 situation, we get 2 totally different looking orbital diagrams in terms of how we populate the electrons into the orbitals. The rule of thumb here is that if you have a strong field situation, we're going to distribute and pair. And if we have a weak field situation, we are going to distribute across all orbitals and then come back and pair after the fact.